Hi all. In the last class, we have discussed what is a topology and what is a topological space and few examples of topological spaces. Topology is denoted by the symbol tau and is a family of subsets of X satisfying few axioms or properties that we have discussed in the last class. And the members of tau are called open sets. Open sets in X. For example, if X equal to set 1, 2 and I am defining a tau as phi X and a singleton set 1. This will satisfy all the three properties of topology and these sets are open. Phi X and 1 are open in X. That means the members of tau are the open sets in X. Now we will define convergence in a topological space. A sequence xn in a topological space x tau in x tau is said to converge to a point y in X if for every open set U containing y, for every open set U containing y, there exists a natural number n or there exists an integer n such that xn belongs to U for all n greater than or equal to n. That means if you have a space x tau and let this be the point y, then the sequence x, there are so many terms in this topological space, assume that, then a sequence xn converges to this point y if for every open set U containing y, xn belongs to U for all n greater than n. Such an n exists. That means infinite number of terms are in this U or in this open set. So that is the definition of convergence in metric space also. Now we will define continuity in a topological space. Suppose there are two topological spaces x tau 1 and y tau 2 and f is a map from x to y and let x naught be a point in X, we say that f is continuous at x naught if for every open set V containing f of x naught in Y there exists an open set U in X such that f of U is contained in V. That means suppose this is x tau 1 and this is y tau 2 and f is a map from x to y. Let this be the point x naught. Then we say that f is continuous at this particular point if for every open set containing f of x naught, for every open set containing f of x naught, we are calling it as V because generally we are taking open sets in the domain space as U and in the range space as V. So for every open set V containing f of x naught, there exists an open set U in X containing x naught such that f of this is contained in f of v. That is, f of u is contained in f of v. In such case, we say that f is continuous at the point x naught. So these are the two definitions came from metric spaces. Next, we will discuss some more examples of topological spaces. First one is every metric space is a topological space because every metric space satisfies the first three axioms of the topology that you can easily verify. Now, a topological space X tau is said to be metrizable if it can be obtained from a suitable metric on X. Then we can discuss. Yesterday we have studied the discrete topology on a set X, and all of you know what is a discrete metric space. In a discrete metric space, dxy equal to 1 if x not equal to y and 0 whenever x equal to y. Now consider an open board BD x naught r. That will be what? That will be singleton set x naught whenever r is less than or equal to 1, and will be the full set x whenever r equal to 1. We know that open boards are open sets. So these are open sets in the metric space X. So singleton set x naught. If this is true for singleton set x naught and we have taken x naught as arbitrary, this is true for any singleton set. Any singleton set is open in the metric space. Now what about the discrete topology? We have yesterday defined discrete topology on a set X as the power set topology. That means if X equal to set ABC, then the topology will be 5X singleton set AB, singleton set B, singleton set A, B, C, and AB, BC, AC. So there will be 2 raised to 3 elements, that is 8 elements. Now we know that the elements of the topology are open sets. This means that these singleton sets are all open. Not only that, this set AB, BC, AC, X5 all are open. Singleton set, all the singleton, what are the possibilities of singleton sets from this set X, A, B, C? Only 3 singleton sets are possible, and all of that are open in this topology. Okay, that means in a discrete topology, every singleton set is open. And see what happens here. Here also singleton sets are open. That means this discrete topology can be obtained from the discrete metric space. And when we say that discrete topology is metrizable. Okay. And if a topology cannot be obtained from a metric space, it cannot be derived from a metric space, we say that that topology is not metrizable. That is not metrizable. Now we are going back to convergence. First, consider the indiscrete topological space. What is the indiscrete topological space? X tau, where tau has only two elements, phi and x. Then let xn be a sequence in X. What are the open sets in X? Only phi and x are the open sets in this topological space. So when does we say xn converges to X? We will say xn converges to X if for every open set U containing X there exists a natural number n such that xn belongs to U for all n greater than or equal to n. But the only open set here in indiscrete topological space is phi and x. Clearly phi does not contain any point. That means x is the only open set in this space. So we have this xn belongs to U. U can be taken as x only. That means xn belongs to X for every n greater than or equal to n. That means what? xn converges to every point of X. xn converges to every point X in X. Is that clear? If you are taking X as 1, 2, 3, 4, then also I am checking whether xn converges to 1. How can I check xn converges to 1? I need to take an open set containing 1. Unfortunately, the only open set containing 1 is X itself. And what happens? Xn should be in X, not only for this n greater than or equal to n, should be for all n in n, for every n, because xn is a sequence in xn. So clearly xn belongs to X. That is very true. That means xn converges to 1. And what happens if I am taking this as 2? Xn converges to 2 because only open set containing 2 is X itself. Clear? So in an indiscrete topological space, the sequence converges to every point of X. That means limit is not unique in a topological space, but limit is unique in a metric space, that we have proved before. Now consider the discrete topology X tau. This is indiscrete. And consider the discrete topology. Now what happens here? If xn converges to X, then for every open set containing X, every open set U containing X, xn belongs to U for all n greater than or equal to n. But singleton set is an open set in a discrete topology that contains X. So X is contained in this open set. This I am taking it as U. And I need to get this. Xn belongs to U. That means Xn belongs to singleton set X for all n greater than or equal to n. That means after some stage, after some finite stage, every element of the sequence should be in X. That means what? Every element of the sequence is X after some finite stage. That is, xn can be of this form, some other elements etc., etc., etc. But after finite stage, every element should be what? X, 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 etc. This sequence we can call it as, or this sequence we know, it is an eventually constant sequence. So, even if xn is eventually constant, then xn converges to that constant. Clear? Now suppose if xn is not eventually constant in a discrete metric space, that means xn is any other sequence, it is not eventually constant and it cannot converge to y, because singleton set y is again an open set containing y, but xn not belongs to singleton set y for all n greater than or equal to n. Why? Because xn, this means what? This means xn equal to y for all n greater than or equal to n. That means you are getting an eventually constant sequence. You have taken this xn as normal sequence, it is not eventually constant. Clear? So this sequence cannot converge to y. Now there is a question whether different metric spaces can induce same topological space. Different metric spaces can induce same topological space. The answer is a big yes. For example, we can consider two metric spaces. One, I am calling it as D1. Let it be the discrete metric on X, and D2 be the usual metric on X. So this clearly induces a topology, and we know that is the discrete topology. Now what about the usual metric D2? For that we can check what is an open set in D2 or an open ball. For that, be D2 XR or X0 R will be what? Set of all y in X such that D2 X0 y less than R, and this will be singleton set X0 if R value is less than 1. That means here also singleton set is open. So this also induces the same topology, that is the discrete topology. Now we will define some more topological spaces. First one, cofinite topology. Cofinite topology. Let X be any set and a subset of X is said to be cofinite if its complement, that is X minus A, is finite. So a set A is said to be cofinite whenever its complement is finite. Let tau be the collection of all cofinite subset of X. That means tau as set of all A subset of X such that A is cofinite together with the empty set phi. Then we can verify this tau is a topology on X. For that, clearly phi belongs to tau because it is set of all A subset of X where A is cofinite union phi. So phi is obviously in tau. And next one is x minus x. What is x minus x? That is phi, which is finite. So this x is cofinite. How do you get that? This is like x minus capital A is finite. That means A is cofinite. Clear? So x is cofinite. So phi already belongs to x. Now x also belongs, sorry, phi already belongs to tau. Now x also belongs to tau. Now second property, let ai, I in I, be an arbitrary collection of non-empty members of tau. These are members of tau. Which means what? Each ai belongs to tau, which implies ai is cofinite, or x minus ai is finite for I in I. X minus ai finite implies what? Intersection of x minus ai is also finite, because intersection of finite set is again a finite set. This will give you x minus union ai by De Morgan's law, which is again finite. X minus union ai finite means what? This union ai is cofinite. That means union ai, I in I, belongs to tau. So tau is closed under arbitrary union. That is the second property. Next, third one, let ai again be the collection of members of tau. ai belongs to tau implies x minus ai is finite. X minus ai finite means what? Union of x minus ai is also finite. That will give you by De Morgan's law x minus intersection ai is finite. That is, intersection ai is cofinite. That means this intersection ai also belongs to tau. Hence, tau is a topology on X, and this topology is known as cofinite topology on the space X. Now what happens if X itself is finite? The given set itself is finite. Then if you take any A subset of X, what will be the complement? X minus A will be finite, because the entire set itself is finite. X itself is finite means if you take any A, its complement, it's also contained in X. That means it is also finite. Clear? X minus A is also contained in X. Since X is finite, subsets of X also finite. So X minus A is finite for every A subset of X. That means every subset of X will be a member of tau. Then clearly every singleton subset is also a member of tau. That means this is nothing but the discrete topology.